So, the group theory, lecture 3. Semester 3. Okay. 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 Fine. So, in my last lecture, I have ended up with the uh, result that, what was my last result? That in Zn, minus 0 class dot, we see that A class belongs to Zn minus 0 class, uh, has an inverse if and only if GCD of A comma n is 1, right? And from this result, we can establish that Zn minus 0 class dot forms a group with respect to multiplication modulo n if and only if n is a prime, right? And for this reason, we have seen that Z6 minus 0 class, Z8 minus 0 class dot, they do not form a group, right? As 6, 8 both are composites, okay, fine, okay. And in this line, we can actually prove that uh, suppose you consider suppose we consider Zn dot, okay, and then we define a set, suppose it is G, and this G constitutes a set of ওকে, দেখা যাচ্ছে তো? হ্যালো, can you see my screen?
Yes, sir.
Okay. So we define the set G, which constitutes a set of those A class belongs to Zn, such that GCD of A comma n is 1. Okay. Then we can see that this G forms a group with respect to the same composition dot, that is multiplication modulo n. Okay. Why? Why does it form a group? Because suppose you have A class and B class belongs to G. Then by the definition of G, you can write GCD of A comma n is 1 and GCD of B comma n is 1, right? And therefore, uh, yeah, so then we have that Ax plus ny equal to 1 and bx dash plus ny dash equal to 1 for some integer xy x dash y dash belongs to Z, right? Using the property of being relatively prime integers, right? Then just multiplying these two equations on each side, then we get, sorry, this ny bx dash plus ny dash, so it will be 1. Then we have, it is ab xx dash plus n into uh, axy dash plus, this will be b x dash y plus n y dash, and this is going to be 1. So you see that, so it is ab x dash, so this is an integer plus n, we can write down this as, suppose it is y double dash, so a x dash plus n y double dash equal to 1, and therefore in view of this you can conclude that, so this implies GCD of AB comma n is 1, and that means AB class belongs to G, right? That is A class dot B class belongs to G. So you see that here the composition satisfies the closure property, right? the composition is closed in G, that is, given any two elements from G, you see that composition of these two elements will again go to the same set G. So this uh, okay. So this says that G is closed under this multiplication modulo n, or you can say that dot satisfies closure property in G. That is, dot satisfies closure property in G, right? Now, since we have seen that Zn dot is a monoid, right? So, being a subset, G will satisfy the associativity, and also since GCD of 1 comma n is 1, so 1 class being a member of G will satisfy the property of being an identity, right? So you can say that dot is associative and one class belongs to G will be the identity in G. So this proves that G with respect to dot forms a monoid. And lastly, you need to check that for any A class belongs to G, this A class must have an inverse. But that part I have already proved in the last lecture, right? That A class belongs to Zn minus 0 class has an inverse if and only if GCD of A comma n is 1. So therefore, with the help of that theorem, that result, you can say that G forms a group with respect to the multiplication modulo n, right? So whenever you are considering Zn with respect to multiplication modulo n, you can always have a group like that, which is comprising of those elements A class such that GCD of A comma n is 1, right? And in particular, whenever n is prime, you know that whenever n is prime, so in particular, whenever n is prime, so Zn minus 0 class will be the G, okay? Okay, 1 minute, please. Okay, fine. Okay. So this proves the case. Okay. Now we shall move to another example, another important example, and this example will have an important role in abstract algebra, since we see that the structure that we are concerned with, that is the group structure in a set. So actually we will see that every group will be a subgroup of some symmetric group. Okay, so that symmetric group that we are now talking about. Okay, so this example is symmetric group, or more generally it is called permutation group. Okay, permutation group. So how one does generate this group? Just have a look at this. Suppose you have a non-empty set. Okay, X, and you consider uh, X, which will be the set of all bijective maps from X onto itself. That is, we are concerned about all those bijective maps defined on X onto itself. That is the bijections from X onto X. Okay, fine. Now we see that if you are considering two maps from a set X onto itself, then you can always generate another map which will be their composition, right? So we would like to impose the operation which is composition of maps. Okay, composition of maps, right, denoted by circle. Okay, then we see that then we see that for any f comma g belongs to Ax, f compose G being a composition of two bijective maps two bijective maps will be a bijection. Again, bijection from X onto itself. That means composition of two members of X will again be a member of X. So that is F compose G belongs to curly X. That means which says that composition satisfies closure property, right? closure property. Or you can say that curly X is closed under composition of maps. Okay. Now we have already seen in the uh, theory of functions mappings defined on sets that composition of two maps, if they can be defined, then this composition will be associative, right? So this composition, so it is known that composition is associative. Okay. And also for any set X, you can always define a map, which is that is the identity map on the set. And also the identity map Ix from X to X will play the role of an identity with respect to composition. That means for any f belongs to curly X, f compose Ix, Ix compose f equal to f. Sorry. Okay. So this proves that curly X forms a monoid with respect to composition of map. Now you know that we know that a map f colon x to x is invertible if and only if f is a bijection, right? And this shows that, for any f belongs to curly X, f inverse exists in curly X with respect to composition of maps as f compose f inverse equal to identity of X will be f inverse compose f. So hence we see that curly X forms a group with respect to the composition of maps compose circle. Okay. And this group is defined as the permutation group for a set X. Okay. So this group is called permutation group for a set X. Okay. Now, if we consider a particular finite set, a particular set X consisting of the points, the numbers 1 to n, or you can also consider any n many objects, suppose a1 a2 n or b1 b2 bn or x1 x2 xn. Okay, just you need to consider n many objects. Okay. Okay, fine. And for our convenience, we are considering these numbers 1 to n. Okay. Then Ax will have n factorial many elements, right? N factorial many elements. Okay. And which will be denoted by Sn, called the symmetric group of order n. Called the symmetric group of order n. Also, any member of Sn will be designated as any member sigma of Sn will be designated as sigma will be just like that 1, 2, 3, n, and you will put here sigma 1, sigma 2, sigma 3, sigma n. Okay. That means for any two members sigma psi belongs to Sn, we we shall we shall designate the composition as sigma compose psi, which will be 1, 2, 3, n, and this will be sigma of psi 1, sigma of psi 2, and sigma of psi n, like that. Okay, fine. And the identity I will be displayed as 1, 2, 3, n. That is 1 goes to 1, 2 goes to 2, 3 goes to 3, n goes to n. Where for every sigma belongs to Sn, sigma inverse will be displayed as uh, sigma 1, sigma 2, sigma n. It is 1 to n, and then you need to arrange sigma 1, sigma 2, sigma n in the order of 1 to n, right? And you will get the sigma inverse for any sigma. Okay, that means suppose uh, we consider S3, that is symmetric group of order 3, then we see that what are the elements of S3? How many elements does it have? 3 factorial elements, that is 6 elements, and one element is the identity, that is the identity permutation. Then we see that the members of S3 will be just first one is identity, that is I, that means 1 2 3 1 2 3, and suppose phi is like that, psi is this, then compose phi with phi, phi square, that is phi compose phi. What is that? 1 2 3 2 1 3 compose 1 2 3 2 1 3. According to the rule of composition, you need to check that. Just start from this side, that is, so you just need to write down all the entries 1 to 3, inputs 1 to 3. Now, so 1, so now start from here, from this side, so 1 goes to 2, then 1 goes to 2, then 2 goes to 1, so 1 goes to 1, then 2 goes to 1, 1 goes to 2, and now for 3 goes to 3 goes to 3. So it is identity. So if you compose phi with phi, it results to identity. Now psi compose psi, what is that? 1 2 3 2 3 1 1 2 3 2 3 1. So just write down the inputs 1 2 3. Now 1, so start from this side, so 1 goes to 2, 2 goes to 3, so 1 goes to 3, 2 goes to 3, 2 goes to 3, then 3 goes to 1, so it is 1. Now 3 goes to 1, 1 goes to 2, so this is again another permutation. Okay, again we compose with psi, you can denote it by psi cube. So then you have 1 2 3 3 1 2, and just put 1 2 3 2 3 1. Then you will see that, so 1 goes to 2, 2 goes to 1, 2 goes to 3, 3 goes to 2, 3 goes to 1, 1 goes to 3. Okay, fine. So it gives the identity again. So psi cube is identity. Okay. So thus, as of now, we have the permutations in S3. First one is I, second one is phi, third one is psi, and then psi square. This is psi square, right? But you have 6 elements, so there are more. So you need to compose phi with psi. That means 1 2 3 2 1 3, and this is 1 2 3 2 3 1. Then what is that? So again write down the inputs 1 2 3 and start from this side. So 1 goes to 2, 2 goes to 1, so 1 goes to 1, 2 goes to 3, 3 goes to 3, 2 goes to 3, 3 goes to 1, 1 goes to 2. And then psi compose phi, that is 1 2 3 2 3 1, and it is 1 2 3 2 1 3, and just have the, okay, yeah, So write down the inputs 1, 2, 3 and start from this side. So 1 goes to 2, 2 goes to 3, 2 goes to 1, 1 goes to 2, 3 goes to 3, 3 goes to 1. Yes. Okay, fine. So thus the members of S3 are. So S3 is identity phi psi, and another one is psi square, and other two was phi psi psi phi, right? And here just look at these two permutations. You will see that these are distinct, right? Phi compose psi and psi compose phi. These are distinct permutations. So that means, so where phi is 1 to psi is 1 to 3, and where phi square is identity, psi cube is identity, and phi psi is not equal to psi phi. Okay. So in this way, you have generated all the elements of S3 symmetric group of order 3, and you have an observation that for these two elements phi and psi, you see that phi compose psi will not be equal to psi compose phi. This property is again an important one in group theory, emerged out from these examples, and this property is called commutativity. So you can define that an algebraic system x dot is called a commutative system or is said to satisfy commutativity if for any two members x y belongs to x, x dot y equal to y dot x, right? So an algebraic system is called a commutative system or is said to satisfy commutativity if for any two xy belongs to x, x dot y equals to y dot x. This holds. And for example, you have already seen that Z plus is commutative, right? Z plus is commutative. Okay. Z minus 0 dot is commutative. Okay. Also, Zn plus is commutative, right? Zn plus is commutative, right? And in Zn dot, in the monoid Zn dot, the group G is commutative, right? But you have seen an example where it doesn't hold. This is the example, right? So in S3, commutativity does not hold. So, but in S3, commutativity does not hold. As we have seen that phi compose psi is not equal to psi compose phi. Okay. So the groups which satisfies commutativity is called, it has some special name due to Abel. It's called Abelian groups. Okay. So you have to define, so a group G dot is said to be an Abelian group if G dot satisfies commutativity, right? That is, dot is commutative, right? That is, for any two elements G1 G2 belongs to G, G1 dot G2 equals to G2 dot G1. And you have already seen some examples of groups in which commutativity holds, such that Z plus, Z minus 0 dot, Zn plus, in Zn dot you have G is a commutative abelian group, right? And also you have seen some non-abelian groups which is S3. Okay. And afterward we will see that actually for any n which is greater or equal to 3, Sn is non-abelian. Okay. So this will be a fact that for n greater or equal to 3, Sn is a non-abelian group. We will prove this. Okay. Fine. Okay. Now if you consider okay, now in Sn, now in Sn, we will see that some permutations are there which has this feature. Which one? For example, in S3 we see that phi. What is phi? Phi was right, this one, right? So that means this permutation will be named as a cycle. It is a cycle. Why it is a cycle? Because 1 goes to 2 and 2 will be returned back to 1. So that is why it is called a cycle. And since there is two objects, so we will say that a cycle of length 2. Okay. So in general, a cycle of length n, length r in Sn is defined to be that permutation sigma where there exists I1, I2, IR such that such that such that sigma I1 equal to I2, sigma I2 equal to I3, and so on. Sigma I r minus 2 is I r minus 1, and sigma I r minus 1 equal to sigma r, sorry, I r, and since it is the last one IR, so it will return back to I1. So it is sigma IR goes to I1. And for other indices and for all other k belongs to 1 to n minus I1, I2, IR, it will fix that k. That is sigma k goes to k. Okay. So that sigma is called a cycle of length r. Okay. And a cycle of length r will be denoted by like this I1, I2, IR. For example, in S6, this is a cycle 1, 2, 3, 4. That is 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 will return back to 1. And other indices, other objects, that is 5 and 6, it will be fixed by this permutation. That is 5 goes to 5, 6 goes to 6. You can also have this one 2, 4, 1, 4, that is 1 goes to 4, 4 goes to 1. Okay. 2, 3, 4 are all examples of cycles. Okay. And we will see that these cycles, the cycles in Sn, have some special character and it will play an important role in Sn. Why? Because any permutation in Sn can be expressed as finitely many cycles, as a product of composition of finitely many cycles. That is, the theorem is that every cycle, sorry, every permutation in Sn can be represented as a product of, product means the composition, product of finitely many cycles. Okay. Distinct cycles. Cycles means finitely many, cycles means finitely many distinct cycles. Okay. Why? Suppose, look at this proof. Suppose you have sigma, right? Sigma in Sn. Then what you do? Okay. Then uh, then we consider these objects. What are those? That is 1, sigma 1, sigma of sigma 1, that is sigma square 1, sigma q 1, sigma 4 1, and so on, right? So you will find apparently that these set of objects are actually, and it seems to be infinite set, but it is not. Why? Because the set on which Sn has been formed is a finite set, that is 1 to n, and these members are always in Sn, in in 1 to n, right? So these sigma 1, sigma square 1, sigma q 1, sigma 4 1, sigma 5 1, sigma 6 1, and so on, these are all in between 1 to n, right? This shows that you will find r comma s such that you will find two positive integers r comma s, I can write z plus, such that sigma to the power r 1 equal to sigma to the power s 1. After some steps, you will see that there are two positive integers for which their powers will coincide. Otherwise, it will go infinitely many times, right? But that is not the case, because we are considering only 1 to n, that is a finite set. And for that reason, you will find R and S such that sigma to the power R1 equal to sigma to the power S1, through which, using the property that sigma is a bijection, so you can always have the inverses, right? Inverse permutations. And then you just impose sigma inverse s many times. Then you will see that you can write down this as sigma to the power r minus s. 1 will going to be 1, right? Right? So we choose the least positive integer, suppose n1, r1, such that sigma to the power r1 1 equal to 1. Okay? Okay? And then the permutation 1, sigma 1, sigma square 1, sigma to the power r1 minus 1, 1 is a cycle of length r1, right? Right? Now, if it would happen that if r1 equal to n, maybe you will see that R1 equal to n, because if you consider a cycle, then that is enough. We are done. So if R1 is n, then just write down this one as P1. This cycle is P1. So then sigma will be P1, right? If R1 is n, then sigma is itself a cycle of length n. Otherwise, if it is not true, then there exists I1, right? So then there exists I1 belongs to 1 to n minus 1 sigma 1 sigma R1 minus 1 1, right? So you will find another positive integer in 1 to n which are not in the set this. Okay, and then you start the same thing as we have done for the previous case. So then you start from I1, then sigma I1, sigma square I1, sigma 2, sigma q I1, and so on. And then again you will find another R2, then there exists another R2 belongs to Z plus such that sigma R21 I1 is I1. So hence, and this gives that, this gives another distinct cycle P2 equal to I1 sigma I1 and so on sigma R2 minus 1 I1. Okay. So if R1 plus R2 equal to n, then we are done. Okay, and sigma will be P1 compose P2, and if not, you just proceed with the same arguments and you will get another P3. Okay, but our set of objects is finite, that is 1 to n. N many objects are there. So this process will continue finitely many times. So since is a finite set, so this process will terminate at some step, say kth step. Okay, that is sigma can be represented as pk. Okay, okay, fine, right. So thus we have proved that any cycle, any permutation in Sn can be represented as a product of distinct cycles. Now note that product of two distinct cycles are commutative. That is, if sigma psi are two cycles, are two distinct cycles, then sigma psi equal to psi sigma. Okay. Okay. Now observe that observe that uh, suppose you have you have a cycle of a cycle, suppose 1 2 3 4 5 in S10. Then we see that this cycle will be actually will be a product of these cycles, which are those product of 1 5 1 4 1 3 1 2. If you execute this operation, you will see that this product is actually equal to this one. And keeping in mind this, we can do this for any cycle. That is, in general, if I1, I2, Ik be a cycle in Sn, then you see that I1, I2, Ik can be represented as I1, Ik, I1, Ik minus 1, I1, I2. This product will be equal to this cycle. So in view of this observation, we can actually have that. So define, so any two cycle is defined as a transposition. Why it is called transposition? Just look at any two cycle. Suppose 1 2. What it does? Just take 1 to 2 and 2 to 1. So that is why it is called transposition. Just changing the position. 1 goes to 2 and 2 goes to 1. Okay. Just you take a flip. Okay. Okay. So any two cycle is defined as a transposition, and the corollary will be, so any permutation in Sn is actually a product of transpositions. Okay, product of finitely many transposition. And it should be remarked that for any permutation, sigma, the number of transposition which constitutes the permutation is unique. That is, for any, suppose you have any sigma, then the number of transposition in which sigma can be represented as a product of transpositions. So this number of transposition is unique for each sigma, and this number, since it is unique, so either it is odd or it is even. So either the number is odd or it is even, right? So definition. So a permutation sigma in Sn is called an even permutation or an odd permutation if sigma can be represented as a product of even number of transpositions or odd number of transpositions respectively. Okay, so if a sigma is represented as a product of even number of transposition, then it is called an even permutation. If it can be expressed as a product of odd number of transposition, then it is called odd permutation, right? So any transposition is itself an odd permutation, right? The identity permutation. I. So actually I can be represented as like this 1 2 2 1. Okay, 1 2 2 1. So it is a product of two transposition. So an even permutation, right? Now since sum up to even permutation, sum up to even number is even, so a product of two even permutation is always an even permutation. Also a product of two even permutation is always even, right? And not only that, product of any number of even permutations will be even, right? And also note that inverse of an even permutation is again an even permutation. Why? As because for any sigma belongs to Sn, sigma compose sigma inverse is I. So since sigma is an even permutation, I itself is an even permutation. So sigma inverse is automatically be an even permutation because sum of an even number and an odd number will be odd. So that is why sigma inverse is eventually an even permutation. So hence, if we define a set an as the set of all even permutations in Sn, then we see that number one, the composition is closed in An. That is for any two sigma psi belongs to N, sigma compose psi is again an even permutation. So sigma compose psi belongs to N. Number two, the identity belongs to N, right? Number three, composition is associative, right? Also, number four, for any sigma belongs to N, sigma inverse also be an even permutation. So, being an even permutation, it will be in N. So, hence, this proves that N forms a group with respect to the composition circle. This group is called, this group An is called the alternating group of order N. Okay. So, with this one, I would like to end today's lecture.